Sometimes we have these tunnels near the station. Sometimes we have near special kind of clients. And offshore, this kind of things happened a few years ago after the cable was built. But you need to take care because the recommendation is to solve it in the beginning. And this, you can see it's a rectangular, this one is a circular, and this one is probably a rectangular too. The first kind, second kind described before. This is a list of description of any technology that I just here resume. Here this the way it's on handbook. Any question and comments about this? If there is no question, I think, and there is a way to use the PowerPoint. I think most of you are aware of this, but there are some space to take notes here. Then after that, you can, in this, you will find some with some, we start looking more to specific elements. Then this specific chapter deals with optical splices, connector, and we call generically passive nodes in a recommendation prepared by ITU. Then we have 6 clauses in this chapter. The first one refers to optical fiber splice. The second one to optical connectors. The third one to passive node elements for fiber optical networks. And I intend to cover these 3 topics this afternoon. We'll have some part to be covered tomorrow morning, and this will be the optical distribution frames, fiber closures and fiber organizers, and passive nodes elements for marinized and submarine optical cables. Then the presentation you are taking copy now refers to the first part, then refers to these 3 clauses. Tomorrow morning we'll have also some topics of chapter 5, and tomorrow afternoon we'll have the rest of chapter 5. Part of this will be present by me and Mr. Kurt, and part will be present by Mr. Makoto, that will arrive this night and is leave after 30-hour trip at least, and be here tomorrow afternoon to meet you. And he will be also responsible for part of the presentation that you have the next week. I'd like always remember you that what we are dealing here, there is a set of recommendations related to this different aspect of optical fiber network. And the first week more related to general aspects and maintenance and cables and fiber and passive elements and some of active elements. The way we put together this will be more discussed in the next week. That's the intention of the tutorial. It's to give you more information. Part of this information you already have, and to give information to prepare to see more and more this system with a general view that considers the procedures, the elements, the systemic vision. This could help the interaction between different people involved in planning and building a network like that and operating the network, and also take more advantage of this knowledge to talk with people more interested in aspects of transmission. This chapter covers these six subjects, each one in each clause, from 1 to 6. And the attention is focused on aspects related to installation, service conditions, transmission, environmental, and mechanical characteristics. That's the way the information were put together, and that's the way we will try to discuss this afternoon. The first element to be considered are optical fiber splices. Of course, everyone knows that splice is a critical point in the optical network. Splice strongly affect the quality of the links and also the link's lifetime. Splices are put in the network to ensure high quality and stability of performance of this point between one another fiber segment during all the time life that the system is expected to work. When we look to optical fiber splice, the term high quality means that we need to have a low splice loss, and also we need to have in that part of the link tensile strength near that to the fiber proof test level. The idea of applying a proof test during the fiber manufacturing is to split the fibers in good piece and use only the strongest part of the fiber that was manufactured. When we put two of these stronger fiber together and do a splice, we want that the splice could be as stronger as the fiber. And the splice is a point that connects two fibers, and it needs to have also tensile strength near what we expect in other position of the fiber. Splice shall be stable over the design life of the system. And under the environmental conditions, we expect the system will be during this lifetime. There are two technologies that can be used for splicing glass optical fibers. The first one is fusion. The second one is mechanical. As the name expresses, fusion means to create a new glass, mixing the glass of the two ends of the fiber. Mechanical means to put the fiber together, not constituting one only segment, but keeping the strength, tensile strength, keeping the loss at this point in acceptable levels. The choice of one or other depends upon the expected functional performance and aspects related to installation and maintenance. Just to give you an example, if we expect that portion where we put two fibers together is intended to still in the same way for a long period, we must use a fusion. If you want to have some points that maybe could be some change in the way, it will not be all the time. Sometimes we can try to change all the apparatus involved, or if we have some cost concerning the choice, we can choose sometimes mechanical. Depends on the experience, depends on the way the people use to deal with the network, and depends on the way the people decide to have one or another way to put fiber together. Optical splice They are designed to provide a permanent connection of single fibers or a group of fibers, generally in ribbons. In the first case, we have what we call optical splice. In second, we use sometimes the term mass splice because the fusion of several fibers at the ribbon occurs at the same time. All optical fiber splice would be suitable for both indoor application and also for outdoor environments. In each case, we need to put the protection with appropriate accessories adequate to the situation. Must take always in consideration that handbook has a lot of useful information, but in each part of handbook there are texts more detailed. In this case, the recommendation L12 and G671, they are two good reference to have more information about this topic. When we think in the first characteristic that we want to have in a high quality level, that is the splice loss, it's good to understand what could cause the splice loss. And in broad way to see the situation is divided in two main categories. First one, as we call extrinsic loss. The other is what we call intrinsic loss. Some better understand could be if we look what could cause sometimes it's called splice loss factor. Then, if we have some extrinsic joint loss factor, someone that want to understand what's happening need to see what is happening in the fiber that are together. In the interface, we could have transverse offset. We can find longitudinal offset, axial tilt, fiber and quality, Fresnel refractions. Just to give you an idea, that's what I mean. If you have two fiber ends, they could be a little far one from the other, and we can find a gap here. It will be the longitudinal offset. You can be some differential in some difference in the axis of both fiber, and could be also one fiber in one direction and other with some tilt direction. Then these are considered extrinsic joint loss factors because they independ of the fiber. By the other way, there are some factors that are directly related to fiber. If one fiber has some fiber diameter variation, considering the core, that's the central region, or considering the cladding, when both are put together, we can find discontinuity. And as this is caused by the fiber, not characteristic, not by the fiber position, is considered intrinsic. Another kind of factor that could cause loss in splicing, mainly in multimode, is the refractive index profile mismatch. We need to have an index profile to have the light guided inside the fiber, and if there's a big difference between one fiber and the other, it causes loss. The mode field diameter, it's the region where the light is confined, also could cause loss if it's some mismatch between the two fibers. And also some geometrical factors, the non-circularity or non-concentricity of the mode field diameter in a single mode fiber could cause some kind of loss. This way, we can generically put the first category of losses related to the technique used to splice. All of these can be controlled, controlling the technique. And the second category of loss is related to properties of the fiber spliced. All of these variation in geometry especially. Yesterday, someone asked me about the maximum value allowed to the loss, splice loss. Imagine you are in the first situation. If you are dealing with this kind of category, it's better to find a better adjustment and remove this cause. But imagine you have factors like this. Then all the new piece of fiber will be almost similar to the first one. Then the people put together, get a high loss, and cut the fiber and put together, and we'll find again a high loss because the diameter of the fibers is relatively constant. And in the first case, the people can work during doing splice and improve the loss of the splice. The second case is not always possible because people could cut several meters and find the same geometry and find the same result. It's why we will be later in this presentation. And it's better always to consider the average of the splice and all the attenuation of the link. Is that clear for everyone, or someone has some doubts about this? Because it's very important to understand what has happened in this splice. Yes, sir?
How can you tell what has caused the splice loss? For instance, if it's an intrinsic factor.
If you are investigating with some detail, the answer could be you could analyze the extremity of the fiber and do geometrical and physical characterization. But most of the time, it's not possible at field. People don't have microscope and so to see what's happening. By the other hand, if you are dealing with the first category, people well-trained, the preparation, good preparation of the machine, and sometimes people could do the splice of 12, 24, 36 fiber at the same time. If most of the fiber are having good splice loss with the same machine, we can consider this is some way controlled. Then if you find one another fiber with high loss, you can imagine that specific fiber is with some intrinsic factors. It's a practical way to do at the field. A lot of bad result, maybe it's necessary to adjust the machine and to find a better position. Sometimes it's better to stop and doing some maintenance on the machine or something like that. If there is a lot of good splice and just some are not so bad, maybe that fiber is not good for this. And of course, the worst case we accept in this is 0.3 dBs. That's if there's something a lot high, it's better to take care. If it's just a slice near this value, one in several, we can sometimes accept, and it's okay. Okay? Yes, sir.
When you say splice loss, I was thinking is splice is joining two fiber together. So when you say splice loss, I was thinking is that loss Or when you join two splice badly, it can cause splice loss. Is it clear? Is it correct? No. Join like this. Maybe any badly is not when your join is not good. I think you can get splice loss. Is that loss?
Yes, that's the amount that we will lose of light because of that interface between the two fibers. In case of fusion, here we have both, but in case of fusion, could be some of these reasons that will result in a not so good, because the idea in fusion is to mixture both. The idea is to mix the core in core of one another fiber and to mix the clad in clad of one fiber in another. Imagine you are not in the same orientation. Part of the core of this fiber will be in contact with the cladding of the other fiber. Then part of the light will pick wrong way, and it will represent a loss. That's that's the idea. Then one more way to characterize this is to just measure there are several practical ways of doing this, but you can the loss of fiber that it's part almost the same amount per kilometer, and here we will have 0.3 dB in a point. Okay, then that is just yes, just this idea. Another question, or can move? Or if someone wants to ask something, we can stop at any moment. Let's look take a look of what needs to be done. Yes, sir?
It's just some clarification about the splicing. Yeah. It seems that most of people have never seen how the work is done. So, reason why he was asking this question, if this loss is due to the bad way doing this splicing, right? Okay, just actually, most of splicing machine used, they have manual mode and automatic mode. So with automatic mode, after to prepare your fiber, the machine is checking if, first of all, the fiber is clean. If it's well cut, or the way you cut it is good. And it's trying to align the both core from one side to another, and the other side, sorry. And then if really the alignment is perfect, the machine is giving you go ahead, or automatically it's joining the two sections. But if you are in the mono mode, it's where you should do those mistakes, because there you are giving command to the machine for joining. So, addition to that, in the machine there is a program which is allowing you to choose the type of the fiber you are working on. For example, you are on the single mode, on the multi mode. There is different type you see, and there, if you don't have the right type of the fiber you are working on it, there you should have problems, because the machine is now doing some work on a wrong fiber. But those losses, even after to do the junction, the machine is giving you the real value for this splicing, the splicing you done. Yeah. So, and there you check if you are under the maximum, if you are in the average, and then you accept it on your redo the splicing. Okay, thanks.
Thank you for this clarification. at the beginning, we are just trying to understand what could be happening in each situation. One of these, we can understand more looking at the methods that exist to obtain a fusion in fibers or on ribbons. Normally, we use what we call a splicing machine. That is, the fusion of the fiber is caused by the electric arc applied in the fiber. Then generically, the procedure is the following. We have two fibers. It's the first activity is to remove the protective coating, because we have the glass portion, and after we have the protective coating. And to do the fusion, we need to have just glass one near the other. And after we need to cleave the fiber. Then we cut the end of each fiber, and then we position and align between the two electrodes. In automatic machine, it was what was described for the delegate. In automatic machine, at this moment, the machine can estimate the splice loss that will be obtained. There are several ways to do this. Some ways more simply compare the position, and considering the alignment, the machine could express as splice loss. Other machines launch some light and measure this light in the other fiber. You can estimate locally the attenuation that will be put, the loss that will be put by this splice. If the user says okay, or if it's automatic, an electric arc heats the silica glass until his melting or softening point. At that time, the fibers are brought together longitudinally in a such way the continuity of the filament is now established, because the melted glass were put together and mixture his interface. And after that, it's necessary to apply a suitable protection device, because in this part we have just the bare fiber, and it's necessary to protect the fiber to allow the handling and the storage without affecting the physical integrity. If we have the fiber just, there are a lot of procedures that are recommended. We will treat it just after these, but just to give you an idea, if the fiber is exposed into ambient, the glass, it's necessary to take control of this surface to have a good level of protection. Some machine has some kind of fiber alignment. It could be a passive. Then in this kind of alignment, we just have the position that could be adjusted, the relative position in both fiber, and other are active. In this case, there is a light injection, a detection system, or a kind of monitoring of the core clad profile. And as your colleague says, in this case, there are an adjustment of position before melt the fiber. Of course, it's more easier to get better values if we have a machine with a good fiber alignment program. Another important point to have in mind is that the cleave quality, and that will give some quality of the end of each fiber, and also the intensity and duration of the arc can be determinant to establish the quality of the splice. The difference of two fibers, of course, influence also. Then we need to have fiber similars. We need to have good end of the fiber, well prepared for this fusion. And we need to prepare to have an arc that is as intense and lasts enough to fuse and to combine the glass of the two fibers. In terms of loss, these are the more important things to have in mind. In terms of long-term mechanical reliability, it's necessary to remove the coating with some care, clean the fiber with some care, and also protect the fiber in a good way, because this aspect refers to the quality of the optical interface, and this aspect refers to the quality of glass surface. The fiber new interface will give us the loss, higher or lower, and the quality of these procedures will make damage or not in the surface of the fiber, and will allow that the fiber stands working well for a long period or not. Any doubt about this? If there is no doubt, we can go to the next set of information. And that deals with mechanical splice. I see there are some interest we can. Well, it's okay. Feel free to share any doubts or any complementary information you think could be useful. We are here to discuss technically this subject, and everyone could give your opinion or do comments. The first we did was the melting of fiber, creating a new structure. The second way to do a splice is using a mechanical apparatus, and this could use different structure and physical design. But every one of these structures or design include this kind of basic components. The first is necessary a surface for a line making fiber ends. After, it's necessary to have a retainer to keep the fibers in alignment. And as we have some open air between the two ends of the fiber, independent how near they are, is useful to have what we call index matching material that creates an interface optical between the two extremities of the fiber. This index matching material is a very important part of the mechanical splice, and generally is used to reduce what we call Fresnel reflection, and shall be chosen to match the optical properties of the fiber. When we buy a set of mechanical splice, this index matching material is part of the kit that we have in hand. Usually this material could be different ones and could be a silicone gels or a UV curable adhesive, epoxy resins, or a kind of optical grease. Someone like gel and grease, they are not permanent, and other like UV curable adhesive or epoxy resins become a plastic in this interface, and they are more permanent. One important thing to have in mind is that index of refraction of these materials, they are very sensitive to temperature. Then they have a higher dependence with the temperature, and this dependence is completely different from the glass. Then when we change 10, 15, 20 degrees, the refractive index of the glass is still the same. When we change this same amount of the temperature, this level, some material of this kind could change a lot their index of refraction. It could be a problem. Then it's very important to take care with the range of temperature that is established by the suppliers of this mechanical splice. It's usually also to have some mechanical splice designed for a low installation on the fiber at the end of the in the factory to fasten joining in field. Some countries, some companies will use this kind of element in the end of the cable. Then each fiber is a kind of element that makes the operation in field easier and faster. This kind of splice, the mechanical splice, it can be used for single fibers or for ribbons. Let's take care about the fiber preparation. There are some steps that need to be carefully followed to have a good splice. The first step is to prepare the fiber, removing all the water blocking jelly in the cable, using paper that could not put extra contamination in the fiber. And sometimes it involves to put the fiber, to soak the fiber in some solvents. It's necessary to take care with the time that we put the fiber in these soaking solvents, because make it easier the removal of the jelly, but it generally could cause some damage in the coating, and this damage could result in some difficulty ahead in doing this procedure. The second step is to remove the coating, and it's better to use a distance recommended by the splice protector manufacturer, and it's better also recommended also to use appropriate tool in order to expose the primary coating. Then we have the core, we have the cladding, primary coating, and secondary coating. And we have the jelly. And the lot of steps we need to establish to reach the position to do the splice is necessary. Prepare the fiber without causing any damage in the other structure will be removed later. The coating removal could be the most critical operation in splice procedure, especially if it has to be performed on fiber that have been in the field for many years. Imagine that case we discussed this morning, that there's a cable cut. It was necessary to prepare new splice. If the idea of this kind of system is to stay in field for 20, 25 years, it's not so difficult to find fibers today with 10, 15, almost 20 years. Then we will find plastic materials like the coating is that are aged for this number of years, and most of the time this kind of aging turns the coating more hard to remove. The recommendation is to do this step carefully because of the final strain of the complete splice depends on minimizing the exposure that can cause flaw in bare fiber. One activity we will realize after the fusion is to apply a proof test in the new surface just to establish the minimum tensile strength of this new fiber created by the junction of two fiber. If one don't do the right thing here, could find a lot of breaks of the fiber during proof test, or it will need to do everything again. To remove the coating, what we call the stripping method, it could be done by chemical, thermal, or mechanical, depending on the application and on the desired performance. Most of the time, the splicing kit have all the way to do this in a good way to keep the characteristics expected for that splice. Just to differentiate both. And you have chemical, the idea is to put the fiber with the coating inside a solvent, and the solvent soft the coating, and the coating is removed. The U-thermal, it's a small oven where we use to put the fiber, and the fiber, including the coating, is heated. It's make easy to remove the coating. In mechanical, it's a kind of device just to cut and remove that portion of the coating that's necessary to do the splice. Sometimes fiber and cleaning is needed most of the time. And in this case, the bare ends shall be cleaned with paper tissue soaked with reagent-grade alcohol to eliminate residual coating, paying attention not to break them or not to damage the surface. The bare fiber ends, that is the end of the fiber without the coating, should be cleaved perpendicularly with respect to the longitudinal axis. Then the recommendation is to cut the surface as a mirror-like without any irregularity in this surface, because that will be the surface that will be put together with other fiber. The first one is just a mistake, and okay, let's pass another. There is some repeated part, but no problem. And then the idea is to mechanically clean the fiber, remove the secondary coating, and there are some recommendation for the angles of this surface. For fusion splice, the idea is to have angles typically less than 1 degree, and for ribbon, they are allowed more than that, around 4 degrees. So, most of the time, the machine helps a lot, more automated and more developed is a machine. This is more a work that is solved during the machine development than in field. These cleaving tools shall be capable to achieve this value with a controlled length of bare fiber compatible with the splice system and protective device. Then is a recommendation that's usually followed by the suppliers of the machine. And for, sorry. there are some differences that can be found in mechanical splice. One is called perpendicular cleavage, typically with the same cleavage angle as fusion splice, and another kind of mechanical splice could be done with angle of at least 4 degrees. Considering the electric arc fusion splicing, it's fundamental to check the performance of the machine. And the conditions of the electrode is a critical factor, and they are sensitive to atmospheric variation. Every supplier of this kind of machine has some recommendation that must be strictly followed by the operators. The optical splice condition, considering arc current, arc time, etc., depends on the characteristics of the fiber as well in the characteristic of the machine. It's why part of the comment, some of this machine could be applied for different fibers. Then there's a way to program the condition of the fiber for that specific, the machine for that specific fiber. It's very important to train well the operators of this kind of machining, because there are a lot of facility. That means that this facility could help a lot in solving these aspects related to achieve a good splice loss, but also if the people don't know exactly what to do, could use the wrong condition, and it's important to train a lot. When I mean train, there are simple recommendations that could be followed. People, before going to the field, they could have some parts of a cable or a fiber that the well-trained people know a good result could be obtained, and just put the new guys doing tenths or several tenths of splicing and looking to the results. It's better to have some time to do this than have a good result in field. Here we have some drawing about some system that could be used. Some machine has some V-groove where the fiber is put, and these V-groove that are aligned one in front of the other. We will have one fiber here, in the other direction another fiber. And other machines use 2 rods, and the fiber is put above 2 rods and have a position. The idea is, when testing the arc condition is completed, just then the splicing can commence. And then the fiber will be positioned on a V-groove of the splice machine. The active alignment machine using a vision system or a local injection and local detection system, and 3-dimensional movements of the fiber to actively align the core or the outside diameters of the 2 fibers being spliced. Then, after take care of all the condition relating to the coating, the surface of the fiber, and the end cut, we test the machine, and if everything okay, the fiber can be put, and in this case, the machine will find the better position of both fiber and give this information to operator. Sometimes the splice is made automatically. Sometimes the operator needs to do some step to conclude the splice. The splice machine minimizes the splice attenuation, and this way focus on the core or cladding of the fiber. And aligning them, or optimizing the transmission line through the fibers and provide an estimate of the optical, the splice attenuation after the splice is complete. Then we have some illustration of this. The idea is to, in this kind of automatic machine, we have one fiber, another fiber, a light source in a detector, and here we have the adjustment of in three position of the extremity of the fiber, the end of the fiber, before conclude the splice. Any question about this? After the splice is completed, it's necessary to check the minimum strain, and it's very important to establish a defined level of mechanical strain for the splice that is related to the expected life of all the other portions of the fiber. And the way of doing this is to perform that's a facility available in some splicing machine to perform this test and to have the splicing checked before to put in the protection in holders for heat shrink protection application. The idea is to compare or to have similar level of proof test applying during the splicing in the same way we did during the manufacturing. The proof test is only application of a certain load in the fiber, the way that fiber that has weak points just break. And then the same could be done with this splice. If the splice have strain below the proof test level, they shall be eliminated and a new splice need to be done. After the proof test, the protector shall be positioned over the spliced point, and this protector is a mechanical device or a form to restore the coating, and both the mechanical and the coating will provide the mechanical, environmental, and environmental protection to the fiber in the region we have a few minutes ago, a bare fiber. There is a lot of different protectors design, heat shrink sleeve, clamp and shell, fiber recoating, recoating device, and encapsulating protectors. All are solutions of engineers to put that portion of fiber in a condition well protected, similar to the other points of the fiber. Most of the protectors are designed for aerial, underground, and buried application, and always it's necessary to put this protector that have the splice inside in appropriate closure. Any question about this? If not, we can go and look more detailed in mechanical splicing. This kind of splicing, the mechanical splicing, allow fixing the fiber in a splice protective housing, generally without the need for electrical power. And they are just mechanical parts put together, and some mechanical splice could be tuned by hand for a minimum splice loss. Then, using some kind of measurement, the operator could change the position and find the better position. And after that, make some action to keep this position. This is an illustration of mechanical splice used in ribbon. Then there is a lot of fibers here, and the ribbon is a set of 4, 8 or more fibers put together, and this is like a flat cable, very small, and it's possible to put this ribbon cable inside a part of a mechanical splice, other ribbon cable on the other side, and have some mechanical device to put together and keep, after adjust the extremity of both in a good alignment. Again, we need to strip and cleave the fiber, and the bare fiber ends are inserted in mechanical housing and checked for their physical contact. For mechanical splice, the proof test is generally not a part of installation because the mechanical structure is a more sophisticated and more strong protection given to the fiber. And sometimes the fiber ends are prepared for splicing by grinding and polishing procedures, especially when this splice is done in factory. Of course, the result of this kind of splice used to be better than the without grinding and polishing. Also, the mechanical splice should be suitable for aerial, underground, and buried application. And the integral housing of the splice could be different for single and multi-splice, providing mechanical and environmental protection. Then in this case, after put together and applied the protection and also the clamps, we have a well-protected structure ready to be used in several different kinds of environment. The index matching material used between the ends of the mating fibers should be chosen to match the optical properties of glass. So in this case, we have an open interface. It's necessary to put the index matching material. The supplier of this material should provide complete information about behavior at different temperatures, especially in extreme temperature, and estimating lifetime in terms of maintaining the initial optical performance. Most of the time, the users, this is a recommendation to the people who manufacture the mechanical splice, and the final users receive this information in a certain way related with all the information of the kit of mechanical splicing. In mechanical splice, the splice protection is built into the splice design, and separate protectors are not required. Remember, when we deal with fusion splice, we need to put the protection after the splice is done, the fusion splice. Here, it's not necessary. Simply doing the mechanical splice, we will get the mechanical protection necessary. As we have splice loss, it's necessary to measure. There are a lot of recommendations that could be followed by the people interested in do a well-controlled network. The first one critical requirement for optical fiber communication system is the total end-to-end loss of each link. Then, considering the number of splices in a link, a realistic maximum value loss should be set. The main point is control the attenuation of the link. The splice is part of this attenuation, but it's more important to control the attenuation of the link than to control the value of each splice by fusion or mechanical. In practice, the field measurement of each splice loss during construction of fiber root could be indicated by the fusion splicing machine, when this machine has a loss estimation, and this information could be used to decide whether the splice should be remade or not. The use of one-way OTDR measurement is not recommended. To characterize splice using OTDR in just one direction, one way, is not recommended. After the construction is complete, the recommendation is that the actual splice loss in the field should be determined by bidirectional OTDR if it's necessary. Some people just decide to control the power using power meter, and if the system has the good attenuation, they don't deal about the measurement with OTDR. Others prefer to have this. It's important to have in mind, if using OTDR, that for single mode fiber, the true splice loss is determined by the bidirectional average of the OTDR readings at the splice. And the idea is to characterize the splice for one side, for other side, and make the average. That average, that will be the value of the splice loss. It's necessary to have bidirectional average because the one-way OTDR measurement should not be used as actual splice loss because of tolerance of mode field diameter and other intrinsic parameters difference in fiber can cause gross error. Then if you look just one side, we can see things that are not happening. In case of the single mode, OTDR single direction reading can be high, being either positive or negative. In addition, any measurable spike from the fusion splice requires that splice be remade. Acceptance level for splice loss depend